Good. So it's a pleasure to welcome Peter Morgan back to Oxford and to the group. Peter was a member of the group. It's been a number of years, hasn't it?
2004, my wife went to Yale.
Yeah. But in the late 90s up until 2004, Peter was a very welcome member of the philosophy of physics group here in Oxford, and he's long had an interest in ways of trying to find ways of thinking about quantum field theory or quantum theory in general that make it look more like classical random variables doing interesting, noisy things. And we have what strikes me as a very interesting latest development of that now. So over to you, Peter, and thanks for coming.
Thank you. It's a pleasure to be back here after 20 years. I'm going to try to show you how I find it helpful to think about quantum field theory in terms of data sets and signal analysis. I'll first jump into algebraic quantum mechanics, which I think of as very much motivated by the kinds of mathematics you get in algebraic quantum field theory, but transposed into the quantum mechanics sort of territory. And classical mechanics can be very much presented in the same sort of way. I'm going to push this as a dataset formalism rather than about ensembles of particles and systems and subsystems. Really try to step away from making the assumption that every event is caused by a single particle. So then I'll jump into a first look at quantum field theory, where the aim will be to nudge us towards signal analysis mindset, but also to nudge us back towards signal analysis, back towards quantum field theory. And in the same vein, to nudge algebraic classical mechanics towards something very similar to quantum field theory as well, what I've called CM+ since 2004, and do that by really using the Poisson bracket to the fullest extent. To do that, well, I will explain later, but also to introduce quantum noise as something distinct from thermal noise. If they were the same, then it would have been very different for the last century, I suppose. But with the introduction of the Poisson bracket used to its fullest extent, that introduces non-commutativity into classical mechanics, into CM+ in particular. That gives a measurement problem, and I found it helpful to look at the difference between CM+ and quantum mechanics in terms of the measurement problem. A few slides about that. But then to also think in terms of signal analysis applied to to how we think about renormalization, to really enter into how that can be thought of as a way to surreptitiously introduce nonlinearity into the Whiteman axioms. Finally, just one slide about a measurement theoretic path towards quantum gravity. I've only been thinking about that for 2 years, so of course one slide is probably more than it deserves. But still we have, I'm not going to say quantum mechanics is incomplete, I'm going to say that classical mechanics is incomplete, the exact opposite of what people usually say. And to do that because, of course, there are no-go theorems that say that there are experiments that can be modeled by quantum mechanics that cannot be modeled by the resources we have available to us in classical mechanics. But with the addition of non-commutativity and quantum noise, CM+ becomes a Hilbert space formalism and operators acting on Hilbert spaces, so that the measurement theory is very much shared with quantum mechanics. And this mathematics is obviously going to follow. So this is too instrumental even for me, particularly the first slide. But I will be a naive realist about experimental apparatuses and about their data sets, because I feel I can kick the apparatus, and I feel that if you don't have a real data set, no journal is going to accept your article about this experiment. It has to be more than just vaporware. And then we'll be able to use, I think, CM+ to push that naive realism to arbitrarily smaller scales in a way that you wouldn't be able to do so in the usual ways of thinking, I think. So I'm going to begin with this rudimentary schematic, where we have a region of space and time here that we want to know something about. So we surround it with devices, each of which is connected by a signal line to a real-time piece of hardware here, and it looks at the signal, and it doesn't record the signal at every picosecond, which would be terabytes per second. Instead, it asks what it can identify in the signal so that it can compress it. And of course, we use devices for which there are identifiable moments when the signal rises suddenly. We say that's an event. We store just the time of that event, typically, and then that gets stored in computer memory. Days or weeks later, we analyze that data. It's not going to change because we put a lot of effort into it not changing. We write a paper, and hopefully it becomes part of our communal knowledge. So there's a particular moment here where the signal is converted from an electromagnetic field, so a current or a voltage, into a digital representation. And that's not something that's movable the way the Heisenberg cut is movable. This is a matter of engineering. Where are you doing your analog to digital conversion? So all we have now is measurements of the voltage in these very limited number of places. It's telling us nothing about the center of this experiment in some ways. And yet we have centuries of experience, of course, of how to calculate what will happen, what would happen if we put a device here, what would be the results for the data set that you would get from that apparatus. So there's a counterfactual sort of element to this that one wants to include in one's analysis. So I think it's helpful to take measured signals instead of measured systems as a starting point. We can work towards measured systems in due course. But as one empirically natural starting point, or indeed a restarting point, it feels like. Because from an experiment, we obtain data sets, terabytes of the things. And those contain lists of numbers. We compute average values, we compute higher statistics, relative frequencies, and so on. So something in the theory should generate those expected averages for future data sets. And indeed, for things we think we're going to be in the future, but turn out not to be because of something gets in the way. So surely counterfactual. So I find it the algebraic quantum mechanics is very helpful because it begins with linear operators instead of beginning with Hilbert spaces as the way that the axioms work. So we can take a linear operator to be used as a model for a dataset average. You can find this in a few places in the literature, but mostly people focus on just the standard way of constructing the axioms. So I'm going to take it that there are abstract measurements really following quantum mechanics, and we're working towards quantum mechanics, and we can add them and multiply them together. So we use a linear operator and the spectrum of linear operator very much as we would a random variable in a sample space to model a particular data set. Then if the algebra is non-commutative, we say it's quantum. If it's commutative, we'll say it's classical. Then we have these four properties which are routine for Hilbert space formalism. I'm just going to assume those. I want to end up at quantum mechanics. Now, of course, that just gives us abstract measurements. It doesn't give us any measurement results. Routine, the standard thing in the literature, is to introduce a state, which is a linear map of measurement operators to expected measurement results, in my terms, to future or counterfactual dataset averages. So for notation, we simply say, well, we have a measurement operator M1, and we're going to apply a particular prepared state rho to that. And as well, we're going to work out the nth moment of that data set as well, using the same sort of structure, but now using the nth power of the measurement operator. So this should all look quite kind of familiar, but also slightly different, of course. But then because we're working with moments, it's useful to introduce a moment generating function. Because I want to be an engineer, I'm a wannabe engineer, so to speak, I'm going to use J for my imaginary all through. So this now is a characteristic function, so we can take the inverse Fourier transform of that and obtain a probability distribution. The routine, again, the literature absolutely standard. There are four properties required for a state. And they really follow the rules for relative frequencies. They should be positive, they should be normalized, and they should be real valued. And you find exactly those properties reflected in these properties for the state. We also expect linearity for the same reason, because expected relative frequencies can be added. And here, even if A and B do not commute, we expect that they will be, this equation will be satisfied. Now, the nice thing about this construction is that because of it, we can use that measurement operators to modulate the state rho, so slipping in a signal analysis kind of language, because this construction here also satisfies the rules for it to be a state. So we obtain a continuum of states. And that's the basis of the Gelfand-Nijmegen-Siegel construction of a Hilbert space. So now we have a Hilbert space, just as we have for quantum mechanics, but what we don't have is we do not have a tensor product, we do not have a partial trace, and I don't propose to introduce either of those here because the axiomatic approaches to quantum field theory do not. Whiteman and Harcastra axioms do not have a tensor product. So finally, for this slide, just to point out that it's a state applied to a measurement operator, the Gelfand-Nijmegen-Siegel construction allows you to write a vector and a covector bracketed around the measurement operator as the same, is expressing the same thing, and similarly for a modulated state. So now that was nicely abstract, but now for what I think is a nicely elementary and concrete matrix model. If you have a measurement M, has this sample space just M1 and 2, you can use an operator M hat that for some basis is going to be diagonal. And so if you want the nth moment of that in a particular state, you take that matrix in its diagonal, then you will pick out the diagonal entries in the density matrix presentation of the density operator, which has these properties, and hence these properties we have. And so this is indeed the nth moment of the data set that we're modeling. Now, if we have a different measurement data set, a different measurement, then the matrix will be diagonal in a different context of the, or can be, I should say, of the same state row. And so it picks out, its diagonal presentation, picks out a different set of probabilities. So what we've got here is we've just encoded multiple probability spaces into a single formal structure. This is entirely classical and mathematics. There's no physics in this, no H-bar. This is just a matrix model of a particularly simple generalized probability theory. So what I think we have in traditional classical physics is we use different initial conditions for different experiments. So you have two experiments and you have the initial conditions. You apply a differential equation to move it backwards and forwards in space and time, and as many experiments you may have. What this operator algebraic structure allows you to do is it gives you more tools for modeling incompatible measurements, because you can put them all together into a single formalism and use a unitary evolution backwards and forwards in time for all of them at once. Of course, you don't actually save anything by doing this, but nonetheless, it conceptually puts them all together in this kind of way. This is something that classical physics can equally well do as quantum mechanical physics, as I think will hopefully become clear as we go through. So now, leaving those three slides aside, jumping into quantum field theory, those ideas hopefully will come through as we go through this. If you look in quantum field theory textbooks, if you've got a scalar field, it's presented in one of the first few chapters as just the inverse Fourier transform of raising and lowering operators. But that's an operator value distribution. It's not a measurement operator. It's not something we can use to describe experimental results. But we smear that operator value distribution with a test function, which is just a function defined everywhere on space and time, Minkowski space. And it's usually required to be relatively smooth and so on. And I'm going to call this, I'm going to denote this M subscript F, because I want to emphasize this is a measurement operator. This is no different from the measurement operators you might use in ordinary quantum mechanics. It need not be. So in the math literature, you'll find f of x is called a test function or a smearing function. But in the signal analysis literature, you find an idea that's very similar, is called a window function. Just how are you looking at the world? And indeed, f of x tells us where and how big and what shape the f measurement is. That's what I'm going to call it all through. Now we can write the f measurement in terms of two components, the raising and lowering operators. And with that, it's really still entirely within quantum field theory, the elementary quantum field theory, so to speak. We can compute the two-point vacuum expectation value smeared by f and g, gives us a pre and a product on the test function space, which is constructed by taking a projection to the forward mass shell and then taking the product of the wave number components of f and g. I'm going to call this the overlap of f and g on some slides, depending on how I'm feeling. So algebraically, all we need to know is this set of four functions, which should look very, very familiar indeed, together with obviously background knowledge, part of which is the Baker-Campbell-Hausdorff identity, which allows us for the f measurement generating function that I introduced earlier in the vacuum state. And that's a Gaussian state, and so indeed we obtain a Gaussian expression for that. And if it's a real value test function, then we can take the inverse Fourier transform of both sides of this to obtain a normal probability distribution with variance given by the pre-inner product of f with itself. This is unfamiliar formalism, but the mathematics is really simple. So now we can construct modulated states. So that gives us a non-Gaussian set of non-Gaussian probability distributions, and it gives a Hilbert space that's just been generated by this f measurement. Whereas if we were constructing a whole Fock space, we'd be using an infinite number of test functions. But this is still connected to quantum field theory because we are working with this manifestly Poincare invariant construction. So now for quantum mechanics, we began with just an index set of measurement operators, 1 through n, just that. That's the index set. But if we want to make contact with a particular experiment, then we're going to need to have a set of descriptions as well as a set of measurement operators. Tell us how to produce those results. So those can be merged together into a single list. So we can use the descriptions as the index set instead of the integers 1 through n. And I do that because that's precisely what quantum field theory does. It takes these test functions as formal, idealized descriptions of how measurements are not point-like, one would say. And I find it very helpful to use this dual formalism because its focus on test functions is mathematically much more helpful because you can multiply those together more or less with complete freedom. Whereas for distributions, of course, multiplication is always problematic. You really shouldn't be doing it at all, almost. So now, again, I find it helpful. You may not, but to think of a carrier signal, the vacuum state as a carrier signal. It's broadband in the sense that any wave number that's on the forward mass shell will contribute to that carrier signal. It's also noisy because we have no phase information for any of those wave numbers on the forward mass shell. So this is intrinsically a probabilistic formalism, and we're going to modulate those probability distributions. So we saw already 2 slides ago that we get a normal distribution for the free field in the vacuum state. But we can also take a G measurement unitary, as I'll call this, and its adjoint and bracket those around the F measurement generating operator to construct this probability distribution, which is just a displacement of the normal distribution that you had for the vacuum state by an amount that depends on the overlap between F and G. So if F and G have a very large overlap, then the displacement will be large. If the overlap is small, then there'll be very little or zero displacement. But we can do more because this is a probability formalism. We can use the G measurement and an adjoint of it and bracket those around the F measurement generating operator to generate this probability distribution. And if we use a higher degree polynomial in the G measurements, then we can construct much more general modulated probability distributions. This is about modulating probability distributions, not about modulation in the same sort of way as you get when you're just listening to music on the radio. Now, everything is constructed, everything's determined by this complex conjugate together with the pre-inner product. That determines the whole geometric structure of any free field. Just the pre-inner product can be different for these, obviously, bosonic. Excuse me. But it's also can be thought of as just telling us how a modulation changes measurement results as we move the two around relative to each other. So because this is a probability formalism, we can talk about joint measurement probabilities. So this, however, I'm going to call a Wigner characteristic function because it's only if all of these measurement operators commute with each other that you'll obtain a joint probability distribution. But in that case, you will. Now, I wanted to introduce the Wigner characteristic function because it is a generating functional form of the Whiteman functions for a Whiteman field in particular. And for the Gaussian case in particular, it's straightforward to just use the big Campbell-Hausdorff identities again to separate out a non-commutative factor and a noise factor that becomes a noise term and a non-commutative term under the exponential that are only expressed in terms of the complex conjugate and the pre-inner product. Let's fix that. But that fixes the algebraic structure. For the geometric structure, we can do that in multiple ways. So we saw already for the Klein-Gordon field that we could project to the forward mass shell. For quantum optics, we can project to the forward light cone, and then we can construct two space-like vectors, 4 vectors, that are both orthogonal to the wave number. And consequently, this construction is also a pre-inner product, with the minus sign is needed because of the metric convention I'm using. Both these, and anything else you would use for a Whiteman field, are manifestly Poincare invariant. Now, if you look at signal analysis, though, negative frequencies are not associated with negative energy. They're not associated with instability or backward causality or anything of that sort. All they're there for is so you can talk about the real signal. You can talk about the cos of omega t plus phi, and so there's positive and negative frequencies in there. Whereas for the analytic signal, as it's called in signal analysis, you have just positive frequencies. Just use x per j omega t. And there's a way of going backwards and forwards between those expressions. Routinely, people work only in the analytic signal and then point back to the real signal. So it's natural for signal analysis to remove the theta k0 here and here, and that has the consequence that the non-commutativity term vanishes completely. So now what we have is an essentially classical construction. It's an everywhere commutative, Gaussian, quantum non-demolition field theory, which is what I'm going to call it because that comes from the quantum computing, quantum information literature. But now this is very different from a thermal state. This is a Poincare invariant H-bar scale noise. because this is a Poincare invariant construction. And that's not how thermal noise is. And we'll come back to that in a little while. So I can show you very explicitly for quantum optics and QND optics how this works through. So we have the usual set of 4 equations for the raising and lowering operators, and we use the pre-inner product from the previous page, and that gives us a non-trivial commutation relation for the measurement operators for quantum optics. But for quantum optics, we can find an involution, bullet involution as I call it, for which this expression is satisfied. That allows us to construct an FQND measurement, as I'm going to call it, where the complex conjugation and the bullet are the opposite way round than they are for the F-bullet measurement that you might construct. And that has the consequence that the FQND measurement has a completely trivial commutation relation. This gives us a commutative algebra. It's essentially classical, but the Hilbert space is isomorphic to what we had for quantum optics because we've used the same raising operators and the same vacuum vector. Now, for quantum optics, we can present this very explicitly. We have the F-bullet involution, you can construct by projecting to left and right holistic components, and then for one of those two, changing the sign in this way, so introducing negative frequencies. And that construction is Lorentz invariant, but it's not translation invariant, nor is it local. So this is going to play through in the mathematics, sure. But both quantum optics and QND optics are Poincare invariant. It's only the relationship between them that is not Poincare invariant. And so this is not a reason to rule out QND optics. And I think by the end, hopefully, it will be clear not to. So clearly, however, the algebras constructed by the FQND measurements and the measurements are not isomorphic to each other because the commutation relations are different. But because this is classical, one would expect to introduce a Poisson bracket to generate transformations such as rotations, boosts, and so on. And if you allow an unrestricted use of that, which I'll explain in a few slides' time, then anything we can model with quantum optics, we can also model with QND optics. We have isomorphisms here. So anything, if you've got a model in quantum optics, you've got a model in QND optics too. So we have the QFT and QNDFT just differ in their commutation relations. But quantum non-diminution field theory, we allow ourselves to use generalized probability whenever it's useful. And of course, it is useful. That's less of the last 100 years. Generalized probability is useful. And so it's also, I think, reasonable to think, well, maybe we could, well, we can, nudge signal analysis towards QNDFT by just introducing algebraic generalized probability and just introducing 1 + 3 dimensions. That's only a small change after all. But nonetheless, if you allow yourself to do that, then signal analysis just becomes quantum non-diminution field theory. Well, I'll show you for classical mechanics, things really do seem as if that makes sense. So I also think of quantum non-diminution optics, however, as like a maximal consistent histories interpretation of quantum optics, where commutativity is precisely what one's aiming for, commutativity at time-like separation, in order to construct a consistent history. But this gives you the whole shebang as a commutative algebra. But it also can be thought of as a little like de Broglie-Bohm, except that this is linear, it's Lorentz invariant, and it's more measurement theoretic. Those are 3 small differences. So now we have, as well, this is absolutely not superdeterminism. And that's because it is a generalized probability theory, but also, and I think more importantly even, we're constructing measurement operators at all scales, but not at a point. Point-like construction is just ruled out by the nature of the mathematics. So how does this play through for algebraic classical mechanics? The curious thing about this is that when we present classical mechanics, we usually do it, commonly do it, as an algebra of functions on phase space. It has 3 binary operations. This is not a simple algebra. Addition, multiplication, and the Poisson bracket. We can't even talk about whether it's commutative or non-commutative because that's for something that has 2 binary operations. So now, we can, however, construct an algebra that does have only 2 binary operations, addition and composition, if we introduce 2 classes of operators, multiply by W and Poisson by W, where we just use the multiplication operator and the Poisson operator in the same way to construct these 2 classes, YW and ZW, where a familiar example of this is just Poisson by the Hamiltonian function, which is the Liouvillean operator that generates time-like evolution. Now, the Jacobi identity gives you in a few lines, gives you this non-trivial commutation relation for the Y and Z operators. So what I'm suggesting is we can use the z's as well as the y's, and it gives us a more powerful structure than classical mechanics, so I call it CM+, so long as we're prepared to use the z operators without any restriction. I'm going to show you in a few slides why we have not allowed ourselves to use n greater than 1 in this particular case. We always exponentiate just zw to the power 1. But that's not what quantum mechanics do. Well, that's anticipating something I'm going to talk about later. So that gives us algebraic measurement theory that's shared with quantum mechanics. We've got non-commutativity, and on the next slide, I'm going to construct a state over a particular choice. And the payoff for this is we can construct isomorphisms instead of quantization and the correspondence principle, which obviously are troublesome precisely because they're not isomorphisms. So I can't present with sort of generality for any algebra. So I'm going to specialize in the simple harmonic oscillator, for which the Poisson bracket is just this antisymmetric form. The multiplication operators, just Q and P. The Poisson operators become partially Q and partially P, switching those two around. That gives us two copies of the Weyl algebra. And we also have for the multiplication by the Hamiltonian function and Poisson by the Hamiltonian function gives us this differential operator. So the place to go for a state is the Gibbs state from the late 19th century. And in generating function form, where again I'm going to use J as my imaginary, is immediately can be written down almost as just a Gaussian state, where now we're using YQ and YP as measurement operators, just as we do in quantum mechanics. But because we've introduced J, we're now working with the Weyl-Heisenberg algebra, for which there's only a very limited range of representations. Those are well presented in terms of just raising and lowering operators, except that here we've got KT where we might expect to see H bar. So we also have a thermal state, a thermal vector, which is annihilated by these lowering operators. So now we can construct a modulated non-equilibrium state, so we can construct a thermal Hilbert space without any H bar at all. So instead of trying to map classical QMP to quantum QMP, which just doesn't work, we can instead map Q and J partially Q, this is the standard representation that people use in any case, to Q1 and P1, and similarly for P and J partially P. However, KT is not H bar. You will see in the literature in places where people just jump to, oh, well, we just put H bar here. But I think that's much too fast. Thermal noise is not the same as quantum noise, and we need to discuss what the difference is. The first difference is clearly that H bar and KT have different units. That doesn't give us anything constructive to go by. On the other hand, quantum field theory is absolutely specific, precise about what we can do with this. And that is that the quantum vacuum is Poincare invariant, thermal noise is not invariant under boost, and the quantum vacuum is where you find quantum noise. And this difference of symmetry properties can be used in CM+, where now H bar is an amplitude of a Poincare invariant noise, and KT is an amplitude of a less invariant thermal noise. So I think this gives us a new reason to think we must work with field theories. So that this talk is about interpretation of quantum field theory, not about interpretation of quantum mechanics, at least not directly. Because we can only define the Lorentz group in 1 + 1 dimensions at least. 1 + 3 dimensions where we will want to work, of course. So for CM+ as well, we should really notice that H bar approaching 0 is no longer a classical approximation, which is routine in the literature, of course. It's become a mean field approximation. It's something one will always want to do because it will simplify the mathematics, but nonetheless, it's not what we should think of as a classical approximation if we're thinking in terms of CM+. So now there's a considerable difference between quantum mechanics and CM+ that derives from the Hamiltonian, from the generator of evolution, which for the Gibbs state turns out to be not a positive operator. As you'd expect, because we're introducing negative frequencies as well as positive frequencies, but this is from classical mechanics end. The Hamiltonian operator in quantum mechanics is bounded below, and that results in analytic properties that we absolutely do not want to give up. So I suggest, however, that we should take CM+ to include non-commutativity and quantum noise. That gives us a measurement theory that's the same as for quantum mechanics. It means we're working with a Hilbert space and operators acting on the Hilbert space. But analyticity, it's useful to just separate them off and say CM+ is a different kind of model than quantum mechanics. So we can model this experiment either with CM+ or with quantum mechanics. But we can say that now that quantum mechanics is an analytic form of CM+. And that's following terminology that you'll find in language you'll find in signal analysis. So how has classical mechanics been straw-manned? I think this is the reason. And that is that if you use ZP, just partially Q, that just generates translations when you use it in a unitary transformation, just subtracts a constant. That's perfectly reasonable. But if you use ZP cubed, which is also anti-Hermitian, generate a unitary transformation using that, you generate a multiplication operator with a differential operator added. Clearly that's not okay from a naive classical perspective. It's very different then. But if you think in terms of quantum mechanics, this is just unitary equivalence. And that's something that we can also use in classical mechanics. And it's just as I showed you for the elementary matrix model on page number 5. This is a useful thing to have available in your toolbox. You don't have to take any ontological perspective to this necessarily. So if we unlock that power for classical mechanics, then the initial condition becomes something much more complicated. You have to use state tomography to determine the density operator. But for that, you get all the benefits of working in quantum mechanical formalism. So it's worth doing when it's worth doing, and when it's not worth doing, well, you don't do it. So as I say, CM+ has a measurement problem because it's non-commutative now. But because the measurement theories are precisely the same, everything I'm going to say in the next 4 slides actually applies to both, and so I won't mention which it is I'm talking about. So if we have 2 measurements A and B, they have different sample spaces, and we present them both in terms of projection, orthogonal projection operators, then if we perform a measurement of A, then we obtain a result alpha M with a probability given by the state vector bracketed around the projection operator, corresponding projection operator. Now if we have 2 measurements, we say that the result alpha M collapses the state vector. So we have psi becomes psi M, which we construct using the projection operator again and normalizing. But now we measure B in that state. So we obtain a conditional probability, which is just given by this expression. So the joint probability is just this expression here, which is constructed using this positive operator here. Indeed, that is a positive operator, given the construction. So we generate joint probabilities for the joint result, alpha M beta N. So instead of thinking of collapse as affecting a state, we can instead think of it as well, I should say, as collapse as affecting the next measurement. So instead of using this operator, which isn't a positive operator in general, this operator, which is a positive operator, so we've modified Qn in the appropriate way. This is really elementary, of course, but nonetheless, I've not seen this in the literature, and this is in the 2022 paper that's mentioned on the previous slide. So then we can use those positive operators to construct a collapse product, a positive operator valued measure, A collapse B, that has a sample space, and we can do that even if A and B do not commute. But now, because we've constructed a joint probability, that's something we think of as essentially classical. Indeed, we can clearly just use commuting operators, A prime and B prime, in a different vector state, psi prime, in a different Hilbert space, H prime. So really rooting everything out and taking a new structure that gives the same joint probability. We've given ourselves ample space here to reproduce whatever the result was here. Now, mathematically, this looks really ridiculously naive, but mathematically, this is to use the Lamarck dilation theorem to construct a joint projection-valued measurement, AB, should we say, that gives us the same result as A collapse B, and it does that by introducing a larger Hilbert space. This contrasts nicely with decoherence, it seems to me, because now, instead of taking decoherence, taking a model for the whole universe and taking partial trace to 2-dimensional Hilbert space, say, we're going to take a small Hilbert space and we're going to make it bigger and bigger and bigger as we need to. So this is much more an engineering sort of approach, it seems to me, to the problem. You use the model you've got. If it works, fine. If it doesn't work, you build something better and bigger. So I've called this the super Heisenberg picture because it applies both unitary evolution and collapse to measurements. So this is a step beyond the Heisenberg picture, and it's a step beyond the Schrödinger picture. But this is not unitary equivalence, it's an empirical equivalence, of course. But nonetheless, we can model the same expected joint measurement statistics. Now, if you don't like the name super Heisenberg picture, I have 5 more names down here based on various different ideas. And I think any self-respecting interpretation should be able to think of a name for this structure as well. But I'm not going to go through them. So for signal analysis, you do many, many measurements at time-like separation. So all of the measurement operators you should be using for those in quantum mechanics would always be non-commuting every single one. There'll be a collapse between every single one of them, or something more complicated than that, strictly speaking. But we can instead use a quantum non-demolition field theory. So we have a different state as input, but we don't have to change it at all. You just set everything up so that you get the same joint probability at the end. This is possible just because of the way the mathematics works, really. And so everything commutes, there's no collapses. So you can still think of collapse as a dynamical process if you like. There's nothing wrong with that mathematics at all. But we can also think of collapse as an algorithm for constructing joint probabilities and for working our way towards quantum non-demolition field theory. So how am I going to use this kind of thinking? This is really a little bit of a break, of course. To talk about the Whiteman axioms, which look remarkably simple, it's always seemed to me. Just 6 statements, as you find in Haag's local quantum physics. And yet, if you look at quantum non-demolition field theory and signal analysis, really almost none of these look like obvious, which for axioms you're expecting that they should be obvious in some sort of sense, I suppose. But in particular, I'm going to focus only on nonlinearity, where we usually expect that the map is an operator value distribution, and so this map is a linear map. And I'm going to just talk about allowing that to be nonlinear. So there's one thing to point out first, which I don't see in the literature very often, or maybe even hardly at all. And that is there are 2 linearities. We have the Neumann linearity, which we need so that we obtain a probability interpretation. So I don't want to mess with that. On the other hand, I absolutely do want to mess with the idea that F measurements must axiomatically be linear in the test functions, so that because of this construction, we have this linearity as well, clearly completely separate from the other. Now, there are 5 slides in the appendices. I'm going to go through this really fast. So for engineering, linearity is always just a first approximation. You look at the system, and if your model doesn't work, then one thing you think is, well, do I have to introduce a cutoff? Do I have to introduce some other nonlinearity? Is the modulation really going to have a linear effect on this measurement over here? Well, almost certainly not. So that doesn't give us much of a guide here, I feel. But if you look at real space renormalization, they're the construction of different levels of dress measurements. Starts at one particular level, but then we do many measurements at a certain level, at that lower level. We combine them together in some kind of way to construct the next level of dress measurements. That combination is never a linear combination. It's always a nonlinear construction. Otherwise, it would just be a linear field, and hence not a renormalization at all, I suspect. Now, for renormalization group, there's a rather different argument that results from the fact that the renormalization scale and the measurement operators both depend on the test functions. If you have a quantum field theoretic model of your experiment, that will be a long list, thousands possibly, of test functions describing how each measurement in the apparatus works. But the renormalization scale, which determines the dynamical equations you're going to use, also depends on what experiment, or details of the experiment. It should also be a functional of those test functions, as well as the kinematic construction of the measurement operators. So it's a double dependence there that, well, perhaps I hope that's not too vague a description. Now, the last 2 entries here are slightly different arguments, and they say that if you rule out nonlinearity, then that rules out, for one thing, holism. This is something that was pointed out by Laura Reschi fairly recent, in the last year or 2. That if you insist on a linear construction, particularly for our Castor axioms, then you're ruling out holism axiomatically. Now, for philosophers, that seems like a real no-no. It may be that the world is truly non-holist, but you can't just assert that by axiomatically. You really should be considering both sets of axioms, both the nonlinear form and the linear form, and see where each gets you to. And the last one is a more mathematical argument, and I won't go through it. So, how do we get a reinvention of interacting quantum field theory from this kind of thinking? If you look in the conventional Lagrangian deformation, you'll see something like this under third or fourth that chapter perhaps. And that's just a construction of a generating functional of a test function j. And you can take a functional derivative of that to construct a 4-point vacuum expectation value, for example, something that's like this. But of course, if you make it Lorentz invariant, then no one's managed to do that and it still be well defined. No mathematician is going to walk away happy from any construction we've got so far. But what we've started with here is a Whiteman field, effectively, a single mass, and so the Riche-Leiter theorem applies. And it asserts that local operators acting on the vacuum vector can approximate any vector. So if we can find a regularization for which this vector is a finite norm in the Hilbert space, we can approximate that vector by a vector that is constructed using only nonlinear local functionals of the test function j. Now, renormalization makes things more complicated, surprisingly, because it introduces mass and length rescaling, but we can accommodate that by just using a collection of different masses. So this index I might be a continuous index, but nonetheless it just says for many different masses. And so now we have to use something which includes many different masses, not just a single mass. Things are going to get complicated with this kind of construction, to be sure. So now we know that we can approximate the physics with a renormalized vector, should we say, and obviously the vacuum expectation value that can be constructed for that. And if we take functional derivatives of that and look at the 4-point vacuum expectation value, then you'll obtain constructions such as this, where this is a pictorial form of the Feynman loop component, a particular Feynman loop component, where you're going to integrate over 10 y variables everywhere in space and time. And so it's an enormously non-local construction. Nonetheless, this object, assuming you've managed to make it exist in the Hilbert space, which is not a given at all, but some regularized form, which is, we can approximate that using a local nonlinear construction. And if you take functional derivatives of that, what you obtain is just a sum of products of many, many overlaps of what I call fragment functionals applied to the test function fi. So here we'd expect to find a factor in a term that says f1 of f1 and f1 of f3, and so on. So this is an inverse problem of sorts. We want to look for local nonlinear fragment functionals and measurement operators that locally approximate what happens in the bulk. This happens in the bulk here, whereas here we're not considering the bulk here because it's all just the vacuum. If it's not the vacuum, there should be another test function in your model. All this works because of the Riche-Leiter theorem. So the interplay here between local and global is rather similar to holography because we're depending absolutely on the analytic structure of the Whiteman fields. So I'm going to show you in the next slide how we can construct a well-defined Poincare invariant fragment resonance theory for which hopefully that construction will approximate the physics. What I hope I've done may not be enough, is to show that an analysis of renormalization and of path integrals shows we should introduce nonlinearity, and that introducing nonlinearity is actually enough because of the Riche-Leiter theorem. To say it again. So now we want to present the Wigner characteristic function in some sort of sense. Well, it must be manifestly Poincare invariant functional of the lambda i's and fi's, and indeed I can show you one way at least in which such a thing could be done. And we want to construct or decompose that function in many different ways, possibly, because one experiment may well be more intuitively modeled by a different decomposition than in the other. So it would be comparable to decomposing in real space or in wavelet space or in Fourier space for a particular experiment. One gives us more intuition than the other. So that gives us, but there's another aspect here that I don't want to prejudge what a better mathematician than myself might come up with for more elaborate mathematics that doesn't use the Wigner characteristic function as a halfway house at all. So for two tentative constructions here, we can construct a recursive cloud following the ideas of effective field theory here, where everything, so we take a particular test function f, we construct a particular fragment functional within it, and then we construct downwards, all the way or just to a finite level. And we can present that as an iterated solution of an integral equation such as this, where that's going to be integrated over different fragments. So with respect to the alpha, instead of over points in space and time. And indeed, this could just be a sum. If a sum works well enough, then that's what you would want to use as an engineer, at least, but also as a working physicist. And I'm going to skip this because I think time is running pretty close. So now we have a very nice, concise list of the difficulties of quantum field theory from an article by Algebraic and Oettinger in 2022. First on the list, rightly, is divergences. What I've suggested is that nonlinear fragment resonance theories can at least address this and do it in a very different way than we're used to, and hopefully there might be other mathematics which would give us a more intuitive grasp on this particular. I really think of this as a halfway house. There's no precise ontological picture, they suggest, but I think a signal analysis perspective, together with the super Heisenberg picture, the quantum non-demolition field theory, and a classically sophisticated view of measurement incompatibility, can address that in ways that have not been present in the literature so far, as I know. There are no particles, but by the introduction of nonlinearity as well as dispersion, which was already there, that gives us the same sort of resources as we would expect to be enough to construct solitons if we were just working with differential equations. And in any case, we've weakened the axioms, so there should be more models. Also, Haug's theorem, I think, is completely transformed by this, because now we have nonlinearity as an extra resource for constructing subalgebras, non-trivial subalgebras of the free algebras. And finally, for the measurement problem, well, I'm completely happy with collapses of joint probability construction as an approach to this. I have low standards, I always say. On the other hand, the super Heisenberg picture and the quantum non-demolition field theory sort of approach also gives us a way of thinking about that without entering into the collapses of joint probability construction. So finally, last slide, how can this be used towards quantum gravity? So at the beginning, I just suggested for ordinary quantum mechanics, we just have a measurement, each one has a description. Now we just want to do probability theory with that, or generalized probability theory. And all we need to construct a Gaussian state is one positive semi-definite, n by n, overlap matrix, where for each pair of operators, you need to construct a number. And that has to fit in the matrix in such a way that it's a positive definite matrix. Well, it is actually straightforward in many ways, as long as you have a pre and a product. But then for interactions, we just introduce and combine many such matrices, while ensuring that the Wigner characteristic function for that state, satisfy the properties for it to be a state. Now, if we want to do quantum gravity, and suppose we do have a successful deformed optics, so this Wigner characteristic function is presented in terms of many overlap matrices, indexed by alpha. So then we can introduce just a new description, which takes that bivector test function, but also adds information about the background, the proportion metricity, so on and so forth. Nonetheless, that information about the background is not information about what background actually is. It's information that the experimenter needs so that they can reproduce the experimental results. So we're backing away from making claims about the ontology behind this. Nonetheless, hopefully, we will find out something by measuring more and more detail, down to the 10 to the minus 1,000 meter scale, I always say, because this is so totally scale blind that you really can talk again about all possible scales. Whether or not they exist, doesn't matter. So then whenever the overlap matrix in the original deformed optics occurs, then we can just substitute instead a new overlap matrix, and that gives us a candidate optics and quantum gravity. Of course, the first one you think of is not going to be right, nor the 100th. But nonetheless, this is at least a well-defined mathematics for constructing such things, and we're not assuming that it's loops or strings or foams or lattices and any of the many, many, many different things which people have committed their careers to without any idea as to whether that's what really happens at the 10 to the minus 1,000 meter scale. I mean, because really the Planck scale has disappeared from this kind of analysis here because we are working with a measurement theory perspective here. It's not working with the ontology at the first. Again, if you do lots of measurements, hopefully we'll discover more and more and more about what there is down there. But nonetheless, we're not going to make any hypotheses non-fingo, I suppose I should say. Notice as well, we're not talking about gravitons here because I've not introduced the tensor product. I've not introduced partial trace. This is a completely different way of thinking about it, purely in terms of field theories. It's not to deny that you can have a particle language, because you can add in tensor products and partial traces. It's just that I haven't in this talk, and yet we can still get a certain distance with this. So I started with really quite a classical starting point. It really should sound quite like Copenhagen in some ways, but I've also analyzed this data in a way that really has emphasized measurement description, which I think is kind of different from Copenhagen in some ways. And I've emphasized as well that we can allow ourselves a classical approach to measurement incompatibility. Just a tool. It's a mathematics. You shouldn't be prevented from using mathematics just because you say, well, I'm classical sort of, instead of quantum sort of. Classic mechanics with non-commutativity, with quantum noise, is something that's powerful enough to describe any system, just the same as quantum mechanics can. So the system is now just the system. You don't say it's a quantum system or a classical system. You just say, well, my model of it is a classical model or a quantum model. Really backing away from making grand ontological claims about what kind of system you've got in front of you. And indeed, there's no such thing as non-classicality if we allow CM+. There's still an idea of quantum in here, however. If your experiment cannot be modeled with a mean field approximation, so the H bar is important because the noise is more important than just mean field, then we can think of it as quantum. That's because this other noise, as well as the thermal noise, acts differently from the thermal noise in such a way that this system, and of course we look for systems for which that is precisely the case. We look for systems where Planck's constant is important to the operation of the device, so that we can do quantum mechanics. I've also argued we can think of renormalization as a surreptitious introduction of nonlinearity into the Whiteman axioms. This is actually what I care about, because renormalization has troubled me for 30 years, as it has many people, I should say. So finally, my reading of the literature on quantum and classical is that they have been converging in many, many ways. And what I'm doing here in this talk and in the last few years is really just trying to push that forward and see where it gets to. This is not a theory of everything. This is a way of thinking about things. It really has no immediate consequences. And yet, well, I like it. Thank you very much.